Let us discuss about the kinetics of zero order reaction and the first order reaction. First order reaction. So we'll discuss about the integrated rate equation. Now first, for the zero order reaction. Now suppose this is a reaction given, R gives P, where R stands for reactant and P stands for product. Then the instantaneous rate of disappearance of R is given by this equation. R raised to power 0, because we have assumed that the order of the reaction is 0, and this is equal to K. It means this rate of a reaction is independent of the concentration of the reactant. So rate of reaction is independent of the concentration of the reactant. This is the first point. Now integration of this is dr is equal to minus k into dt. So on integration, this is the concentration of the reactant at t equals to 0. That is called initial concentration of the reactant. And this is the concentration of the reactant at the end of time t. It gives R minus R naught is equal to minus of K into T, or we can write that R is equal to R naught minus K into T. Now this is very important equation. This is equation number 1. If we plot a graph between the concentration of the reactant R against time, then the graph is a straight line and the intercept is equal to R naught, and the slope of this line is equal to minus of K. So if any reaction has a graph between the concentration of reactant and time straight line with slope equals to minus K, it means it's a zero order reaction. So K is equal to R naught minus R upon T. This is integrated rate equation. This is number 2, called the integrated rate equation for a zero order reaction. Now examples of zero order reactions are: the first is the decomposition of ammonia in the presence of a platinum surface. This is zero order reaction. Decomposition of Hi into hydrogen and iodine in the presence of a gold is an example of a zero order reaction. Then we define a term called half-life. T half means the time for the reaction to be half complete. Time required for the reaction to be half complete, means the 50% complete. That is called half-life. And for a zero order reaction, this half-life is equal to R naught upon 2K. So this is half-life formula for a zero order reaction. Now we discuss one question. Suppose this is the reaction given: decomposition of ammonia into N2 gas plus the 3 hydrogen gas, and this reaction has a rate constant equals to 1.23 into 10 to the power minus 2 moles per liter per second. Now if you have to find the rate of formation of nitrogen or rate of formation of hydrogen, we write rate as minus 1 by 2 dNH3 by dt. This is instantaneous rate of disappearance of ammonia plus the instantaneous rate of formation of nitrogen equals to plus 1 by 3 dH2 by dt, and this is equal to K into ammonia raised to power 0, because it is a zero order reaction, and is equal to K. So the instantaneous rate of formation of nitrogen is same as K and is equal to 1.23 into 10 to the power minus 2 moles per liter per second. And the rate of formation of hydrogen, instantaneous rate of formation of hydrogen is equal to 3 times K, and this is 3 into 1.23 into 10 to the power minus 2, and this is equal to 3.69 into 10 to the power minus 2 moles per liter and per second. So this is about the zero order reaction. Now next is the integrated rate equation. Integrated rate equation for a first order reaction. This is very important first order reaction. Now this is a reaction given R gives P, then we write instantaneous rate of disappearance of reactant is equal to K into R raised to power 1 because the order of the reaction is 1, and this is equal to R. Now integration of this gives, this is 1 by R dr is equal to minus K into dt. Now we're integrating. When the t equals to 0, we have an initial concentration of the reactant R naught, and at t equals to t, at the end of time t, the concentration of the reactant is R. Now it gives natural log R minus natural log R naught is equal to minus of K into T, or we can write log base 10, and R means the initial, R is the concentration of reactant at the end of time t, R naught is the initial concentration, and this is equal to minus of K upon 2.303 time, and just rearrange the terms, it gives log of R is equal to minus K upon 2.303 T plus log of R. Now this is very important equation number 1, and if we plot a graph between the log of concentration against time, it gives a straight line with negative slope, and slope is equal to minus of K upon 2.303. So if we know the value of the slope, we can calculate the rate constant, and the intercept is equal to log of initial concentration of the reactant R. And the rearrangement of this equation gives the integrated rate equation. K is equal to 2.303 upon time log of initial concentration upon the concentration at the end of time t, and make sure this R naught has to be greater than R, and this R is the concentration of the reactant at the end of time t. At time t means how much reactant is left at the end of time t. How much has been converted into product, that is not important. Now the half-life expression for the first order reaction is this. Now half-life means when the concentration of the reactant is reduced to half of its initial value. So if we assume that this was the initial value, now at the end of the half-life only half of this is left. Now T half is equal to 2.303 upon K log of 2, and log 2 is 0.301 upon K, and this T half is equal to 0.693 upon K. And since no concentration term is involved in this, there is no concentration term, it means the half-life of a first order reaction is independent of the initial concentration of the reactant. Initial concentration of the reactant. So if we plot a graph between the half-life and the initial concentration of the reactant, the graph will be a straight line, and if any reaction has a graph like this, it means the order of the reaction is 1. Now all nuclear disintegration reactions nuclear disintegration reactions are first order reactions. First order reactions. Now another example is this decomposition of the N2O5. It follows a first order kinetics into NO2 plus oxygen gas. This is also a first order reaction. Now other useful results of the first order reaction are and you can use these results directly in the questions. One is that T 3/4 means 75% completion is equal to 2 times the T 50%, and T 99.9% is equal to 10 times T 50%. So these are some useful results of the first order reactions. Now one question is this: a first order reaction is a half complete in 40 minutes. Calculate the time for the reaction to be 80% complete. Now log 5 value is given. Log 5 is equal to 0.70. Now first is it's a half complete, so the half-life is given. It's a 40 minutes. So from this we write the expression for K 0.693 upon 40 is a minute inverse. Now our aim is to find time for the reaction to be 80% complete. It means 80% of the reactant has been converted into product. So only the 20% of the reactant is left behind. So 2.303 upon K log of, if we take initial it was R0, only 20% of this is left behind. Now this is equal to 2.303. Now we put the value of the K 0.693 upon 40. So 40 comes in the numerator and this is log of 5. Now T 80% is equal to now 40 divided by 0.30 into 0.70. So this is equal to 280 upon 3 and this is 93.33 minutes. So this is the kinetics of the zero order reaction and the first order reaction.